once you build a component, so let's say a multiplexer, to prove that it's nothing but ands, ors, and nots, then you can start using them. Now, you could build them from scratch every time, but we like to abstract things. So if we've got a device that does one specific thing and we're going to reuse it over and over again, we can make a new symbol for that and say, okay, that's all of that stuff we did over and over again. So we can kind of make an object out of that. So let's say that flip-flop. Instead of building it from scratch, ands, ors, and nots, over and over again, we could, draw a box and say all of that circuitry anytime I say the spots. And we're able to abstract it and make clearer schematics. So since we've done a flip-flop from scratch, we can start using flip-flops. So let's go under here, kind of close to the simulate button. Let's look under flip-flops and let's bring out that flip-flop D-pit. Okay, let's just put it there to look at for a second. All right, so this has all of the stuff inside of it that we built before, plus, 2 extra little pins that we'll talk about. But instead of having to, have 10 components, we can represent that whole piece of a circuit with a square, and it acts the same way as if we built it from scratch. And you'll do this a lot if you're going to do any digital design, because you're not going to build the components from scratch. The reason you do it here is because I want you to understand what is actually going on inside of them. Okay, so we've built a flip-flop before. The only thing different about this than what we built is this PR and CL. All right, so PL is a preset and clear is clear. So we can drive this to 1 or we could drive this to 0. Now, you see that they're active high. When you've got a circle on an input or an output, that means that it's inverted. Okay, when you see a line over some letters, that means it's inverted. And, I've had some questions about that, like why would we want that? And sometimes it's because it's simpler to have things being driven low. Sometimes it's by nature of what the design is that, you might have 32 outputs and only one of them would be low. So as opposed to saying all of them are on and then that low one being off, we can flip the script and say that it's active low. So that thing that's going on that's different is going to be represented by 0 instead of 1. There's multitudes of reasons, basically coming down to simplicity of design, and sometimes it's easier to interface things when we get a low coming in so that we're, syncing instead of source and current. Okay. So the only thing that's really different about this flip-flop, ignore the PR and the CL for now, okay, is this clock, okay? Instead of having an enable like we built before, it's got a clock, and it's represented by this little triangle. And what that represents really is instead of it being level triggered, it's edge triggered, okay? So if we do a level trigger, that's extremely slow, because a level could be a level for a long time. The transition between low and high is usually very, very quick, okay? So we like to do things really quick, so we like to catch things as they are, on edges a lot, okay? Let me show you how that's built. Now, I didn't put it into the flip-flop that we built because Deeds simulates a little bit funky, so we're not going to be able to see the simulate. But let's talk about how we can do something only on a transition as opposed to it being high or low, okay? So if we took an AND gate and we said that the only time that we get anything, a 1 out of this is if both of these are true, and I put an inverter on one of the inputs, I don't know why my should be Control W. Okay. Let's say I had an AND gate and I put a little inverter there, and then I had one input. You should look at that and go, Robbie, that is never going to come on. Okay? And in thinking about it, like, if this is a 0, this is going to be a 1. We've already got a 0 on an AND gate. We're going to get a 0 out. If this was 1, the inverted part of that would be a 0, so it shouldn't be. Now, Deeds wasn't quick enough whenever I started doing this, so I don't know if it is. I'll leave it to you to see if it'll actually do it. But even if it did it, you wouldn't see the 1. But you would get a 1 out of this very quick. Reason being is digital logic works pretty quick. I mean, like, near about the speed of light quick. You know, the speed of electron quick. But electrons still have to take a little bit of time. So whenever I pop this 1, it's going to go through this line without a problem. It's going to go through this, not this inverter without a problem, but it's going to take just a little bit more time to get through it. So as soon as I go from 0 to 1, I'll get a 1 right here. And then this will be a 1 going through this inverter, and just by slowing it down just a little bit through what we call propagation delay, there's a split, just millisecond, microsecond, just a tiny little fraction of a second that this signal gets to this AND gate before this one does. And what that does is, let's say that it's 0 right now, so we've got a 1 right here, right? As soon as we flip it to 1, it hits this hard core, and that's a 1. And it takes just a slight amount of time to get through here before this becomes a 0. So for just a snap, we've got a 1 waiting right there when this gets here before this has a chance to flip. So now we're going to get a little ping 1, and then as soon as it gets through that inverter, it's going to go back down to 0. So we're going to get a little spike, a little beep, little blip, where we get a 1 every time we get that low to high transition. And this is called edge triggering. Now, we're not going to be able to simulate it because we're not able to see how quickly that, we're not able to perceive things at the speed of that propagation delay. But however long it takes to get through that inverter is how long we're going to get that blip. Okay, so that's the only thing that's changed out right here. Now, I'm going to show you something because we're kind of, winding down. Like, if you go up here to learning, like if you love this like I do and you want more, Deeds is free. You can go up here to Deeds Demos, and it's got just tons of circuits that you can build and look at. And you've got Deeds Learning Materials. Okay, so this is some really good stuff. But let's look at this D-latch flip-flop. Let's go down to this D-pit. Okay, so we get a clock that's going to go in. Then we've got a gate, so whatever our data is. We've got a preset and a clear, and then we've got our output and our inverted output. All right, since these are active low, That means that if we want to clear it, we need to put a 0 in. We don't want to clear it, so we put a 1 in. If we want to preset it, we'd put a 0 in, which means it's just going to drive it to 1 regardless of what we're telling it on the other part of the circuit. We would drive it with the 0 because it's, inverted logic right there. Okay. So to make these work, we're going to have to put switches on here and just drive them to 1 to make this work the way that we want it to. Okay. So let's go ahead and use our flip-flop. All right, so let's go and put 2 input switches. Let's go ahead and put 3 because we know that we're going to need 3. All right, since we've got an edge trigger, let's put another input, but let's put it as a input push button. Okay. So that's going to be our clock. And then let's go ahead and put test LED right here and test LED right here. Okay. And then we'll go into our wire. And make our connections. Okay. The only thing different about this is that preset and that clear, which and the edge trigger as opposed to level trigger. Like we built this with nothing but ands, ors, and nots. I can go in, you can go into learning and see what the inside of this looks like. And all the preset is doing is like loading the output with a 1 regardless of what's going on in front of it, and all the clear is doing is driving it with a 0. Okay, so let's look at how this works. So go ahead and simulate it, and we're going to save this as your last name, and then let's save this as counter, because we're going to start building a counter with this. Okay. Now, when we first start simulating, we don't know what the outputs are going to be because we are driving it with a preset and a clear right now. If I turn this to a 1, since this is, negatively triggered, that means that we're not driving it with the clear. All we're doing is driving it with the preset. So no matter what we do with the circuit, it's always going to be a 1. Now, once I go and turn that off, it's just going to retain whatever it's got in it. We latched it in. All right, now, if I go over here and I'm changing this data, so say that we have a bus and that data is changing. The only time that it's going to take data in is when we got a clock signal. Like I pushed and boom, I got my low to high transition. I clocked that 0 in. Boom, 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 boom. Okay. So anytime that clock signal goes high on that little transition, we're going to clock that data in. Now, what I want you to think about is I asked you to learn how to count from 0 to 15 in binary. So we've got, 0, then we got 1, then we got 1, 0, 1, 1, 1, 0, 0, and we keep going. I want you to write that out. Pause the video and write that out right now. And I want you to come back to it when you're done. Okay. Now, I want you to look at the least significant bit. And I want you to look at the pattern that's going on. It's going 0, 1, 0, 1, 0, 1. Verify that. Now I want you to look at the column to the left of that. What's it doing? It's doing 0, 0, 1, 1, 0, 0, 1, 1, and it's going to keep going. Now I want you to look to the column to the left of that. You should see 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, and that's going to go on for infinity. Then if you kept going, if you made a column again, that would have 8 zeros and then 8 ones. If you did it again, then that would have 16 zeros and 16 ones. Now I want you to think about what those columns are in relation to each other. When we have a 0 to 1, and then the next column changes, what we're really doing as we go to the left is we're dividing by 2. Okay? Like every time the column to the right of it does something twice, we do something one time. Okay? So if you need a pause to, let your brain breathe, I know that it probably just exploded. Okay, so we have a low to high transition, and then as soon as we go back, the thing to the left of it is going to change. Okay? And that happens every time. Don't think of the 0, 0, 1, 1 as being separate zeros and separate ones. It's just going to stay 0 and then stay 1 for double the amount of time, right? And then the thing to the left of that is going to stay 0 for half the time or double the time that the thing to the right of it is changing. I want you to stew in that. If you got to pause, walk around outside, hug your pets. I know that it's a lot to take in. So if we want to make a counter so that we can just take an oscillating bit that's going low to high, low to high, low to high, all we really need to do is, take that first bit, and we'll say that is our least significant bit. So we've got something called an oscillator, and it's just going to go low to high. So we'll say that's our least significant bit. All right, so 0, 1, 0, 1, 0, 1. Okay? And then we'll divide that frequency by half. And then, that least significant bit will be going 0, 1, and then we're dividing that frequency by half, and the next one will be like 0, 1, 0, 1, 0, 1. And then we'll divide that by half and be like 0, 1, 0, 1. So how do we divide with ands, ors, and nots? All right. You know that we have nothing but ands, ors, and nots in this circuit right now. We abstracted it so we don't have to get confused looking at the minutia of it anymore, but we know how to build this. When we need to oscillate, we utilize something called negative feedback. So we're taking the output of the signal and doing something to it and feeding it back into the input. All right, so we could take the output of the signal, invert it, and feed it back into the input and use that propagation delay to make it change every time we touch it. Okay, so let's go out of simulation real quick. All right. And we're going to kill this input right now. Okay? So delete it. And we're going to feed the inverted output back into our input. Okay? So let's go ahead and get a... Come on now. We've got this Q0 output, which is just the inverted output. And we're going to feed this back into here. And I want to think about what's going to go on when we do this. If we have a level trigger, we're going to have a problem. Okay? Because if we have a 1 right here, we're going to have a 0 out here. And we've got a wire that's connecting a 1 and a 0. And that's problematic. Okay? But since we have an edge trigger here, as soon as I trigger, whatever this is right here is going to propagate. So let's say that we do have a 0 here. It's going to propagate through here. It's going to take a little bit of time, and it's going to turn this into a 0, and it's going to turn this into a 1. Okay? And while it's doing that, this edge trigger has already triggered. So now this becomes a 1, and it's going to feed the input. So every time we clock in, we're going to propagate whatever's on this input through here, and it's going to wind up flipping. Okay? Because we're feeding the whatever the output is not, right? It's easier just to look at, okay? All right, so right now we have a 1 on here. As soon as we clock this in, it's going to drive this Q to a 1, and it's going to drive this to a 0. And that's going to drive the input. So it's going to be waiting on it's going to have a 0 waiting on it for the next time we clock it in. Okay? And since we have that slight propagation delay, those 1s and 0s, like the one that we had in here, is going through here by the time it gets, to a 0 out here, or, the 0 we had out here is getting through here. By the time this flips, this has already closed that gate. Okay? If you have a 1 and a 0 on the same wire at the same time, you have a problem. Okay? You have a short. That propagation delay makes this work. Okay? Like, it's just a split, little fraction of a second where this is going to be, the same, like, it's just going to be easier to watch. Every time I push this, we're going to be flip-flopping between our two. Alright, so let's get that as a 0 real quick. Alright, so we've got 0, 1, 0, 1, 0, 1. Okay? Now, if we fed this output into another clock input, so let's go ahead and take another one. Alright, I don't want to make a bunch of extra switches, so we're just going to have one clear and one preset for all of them. Okay? And what we're going to do is we're going to feed that output into the next clock. Okay? Before we do that, let's go ahead and take a test LED. Put it here. And then let's do our Control W. I'll feed the output of this into the clock of this. We're going to see what's going on with our output over here. We're going to take that negative feedback that we talked about. All right, so how do we do math? Well, right now we're about to divide. Okay, we're going to turn off the clear and the preset. Now watch what happens as we go out. This is going to be changing at half the speed this is. Okay, so we got 0, 1. That changes. 0, 1. That changes. 0, 1. That changes. All right. Let's do one more just to kind of go out of simulation. Do Control C, Control V. We've got another setup like that. Control W. Going to tie these in. And we're going to take the output of this and we're going to feed into here. All right. So if you don't know that we're doing math right now, we're doing math. We're doing a divide by 2. Let's go and drive our preset and clear. All right. Let's go ahead and clear all of that out. All right. So this is what's called asynchronous. Like this will happen regardless of what the clock's doing. All right. So synchronous is we're having to deal with that clock. We can drive everything asynchronously down to 0. So we got 0, 1, 0, 1, 0, 1, 0, 1. Notice that every other time the thing before it changes, the thing after it changes. Okay. Now, this is one of the reasons that like active low is a thing, because right now like a 0, 0, 0 would be all these as being 1. All right. If we go in and tie off of the inverted inputs and we switch them around, because this is going to be our least significant bit right here, okay, then this is going to be a little bit more significant and this one's going to be a little bit more significant, because this is changing a lot quicker than these, right? So this would be your rightmost bit, or let's say our clock is our rightmost bit. What I'd like to do, so we're going to take a 4-bit output array, and we're going to put it here, okay? And we're going to move our bits so that they look the way we want them to look. All right, so we're going to take our clock, which is just an oscillator. It just goes back and forth, and we can make those many different ways. We can make a flip-flop. That's an astable multi-vibrator. And that's just going to take feedback from itself, and it's going to charge and discharge a capacitor, and we're going to get a low high. When you were in AC fundamentals, you built a tone generator, and all it was doing was using a 555 timer, which is, just comparator flip-flop that charges and discharges a capacitor over and over again. And if we do that in a frequency that we can hear, we got a tone. Or we can take, a crystal and put a voltage across it, and it's going to vibrate at a certain frequency. That's what watches use. You see quartz movement, quartz, that's a crystal, and we can get crystals that vibrate at certain frequencies. and get very new age with it. But at its heart, we take something that's, going low, high, and we're dividing it down to something that's usable for our frequency, and then we're using that as a clock, okay? So right now, we're the clock. When we're pushing this button, we're driving the least significant bit, okay? And then what I want you to do, just trust me on this, is let's take the normally, or the inverted outputs of those. All right. Let's flip them around so they look like what we think of were least significant bits on the right. Go ahead and simulate that. All right, so we've got our clear and our preset. All right, so I've got 0, 0, 0. Then I push this. We had something squirrely because I guess I pushed it twice. But notice what's going on down there. I'm counting in binary. 2, 3, 4, 5, 6, 7, 8. If we ignore this right here, because we're getting it, let's take that wire out real quick, because we're getting a little stutter because, these are all edge triggered and my finger is not, all right? So if we just look at these 3 bits right here, so we'll ignore this one. We're going to say that this is our least significant bit. We got 1, 2, 3, 4. So 4 is 1, 0, 0. 5, 6, 7. Then we're wrapping back around. If we have more bits, that extra bit would be on, and we could keep counting 8, 9, 10. Like 8 would be 1, 0, 0. And so that would stay 1 for a while. 9 is 1, 0, 0, 1. Or 1, 0, 0, 1, yeah. So imagine there's a bit over on the right that's a 1 now. But this pattern will keep going for infinity, right? All right. So we've got 1, 2. 2 is 1, 0. 3, 4, 5, 6, 7. And if we had another bit, we could flip that and keep going. But that pattern is going to keep going forever. So you just made a counter, okay? All right. So I want a full 4-bit counter, and I'm not going to use my button as part of that. So what we're going to do is we're going to stop it. We're going to move this over 1, right? Go ahead and delete the wires that I had coming from my button. We'll just ignore the clock, right? Since it's not edge triggered, we're getting a little funkiness right there. Let's put in 1 more of these. So we're going to do Control C, Control V. I'll pop that right there. Escape. Do Control W, get my wire. We're going to connect these presets and clears. realize that, like Control Copy, Control C, and Control V for paste is a very valuable tool. Like I get used to some keyboard shortcuts if you plan on doing anything with the computer. Alright, so preset it, clear it. Now we've got a 4-bit counter. So we got up to this point right here, and then we started over when we only had 3 bits. But look at it. Now we've got an extra bit. Give me just a second. Now, ignore that bit and notice that cycle keeps going. Like that pattern will keep going for infinity, right? And then if we had an extra bit over here, that would become 1. All of these would reset and that pattern would go on forever. So no matter how high we want to count, we just keep adding. Every flip-flop that we've got will double the amount of numbers that we could count up to. Alright, so, take a video of this working. That's going to be part of it. I don't want to delete this, but I do want to go in here. Now that we've built that, we can use that. Alright, so if we go here, we go to counters, we go 4-bit up, we put it in here. Alright, so we abstracted the flip-flops and made them a square. So we didn't have to, look at a bunch of ands, ors, and nots. We could take this whole thing, and if it's useful to us, abstract it and say every time I want to make a counter, I'm not going to build it out with ands, ors, and nots, or even just flip-flops, and realize that what it takes to do that is in here, but it's a lot less cluttery. Okay? So let's go ahead and take another push button. We're going to drive that clock. And we're going to take a switch. We're going to make it so that we can not have a clear. We're going to take wire here, turn it there, wire there, there, and then go and get another 4-bit output array. Just tie it in there. Alright, so we could have used this like to start with. A lot of people, okay, well, I know how a counter works. Well, do they? Or, if we ever, post-apocalyptic world and they're giving tests on how to rebuild society, like, that box ain't going to do a lot. Like, you can build an AND with switches. You got switches in series. The light bulb's not going to turn on until all of them are turned on. You build an OR gate with switches. Flip any switch. If it's in parallel, the light bulb's going to come on. If you got a test and somebody asks, do I understand? Do you know counters? You can say, I can build one from scratch. Right? Because we did. But now we get to, enjoy the fruits of our labor, and we can use one while still actually knowing, how it works. Like for real knowing how it works. Alright, so this TC output is if we want to chain this into another one, so we could have that driving another counter. So as soon as this gets done, that would go high, and then whenever it gets done again, that would go low. Think of that as an extra, like a more significant bit than the counter, and we could drive other counters with that. Or if we need a 5-bit counter, we could just use that as our most significant bit. But right now, we're not worried with it. We're going to go unclear that because it's active low. So if we have a 0 there, everything's going to be cleared. And as we pulse in, that we've got a counter. Okay. So we're already at 40 minutes. Like, we didn't quite get as far as I wanted to, but I do want I want you to think of the power of this. Like, if we had a counter in there and it's just going up, that could represent, steps. On step 0, I want you to do this. On step 2, I want you to do this. And we could start having things sequentially happen. And so, with the Azores and knots up to this point, we've built, pretty instantaneous things. The output was, dealing with conditions of right now. Well, with the counter, we can start doing things in sequences. So let's say that I wanted something to happen on step 2, okay? And I wanted something to happen on step 5, okay? All I'd have to do would be decode a 2, okay? And then have that happen. And then tie it to this, and every time that I get a 2 out of the counter, that thing happened. What about a 5? Okay. All right, so let's do that. Like, I want to, get you something just a little extra. So I said 2. 2 is 1 0, right? When we're talking about this 4-bit counter, 2 is 0 0 1 0. Okay. If I just tile for the 1 and the 0, then it would do 2. It'd do 6. It'd do any time that the 1 and the 0 right here were true. So if we only want it to happen on 2, we're going to have to read all of those inputs. All right, so 2 is when the least significant bit is 0. Let's put the least significant bit on the bottom. When the second bit is 1 and the other 2 bits are 0. Okay? So all we're doing is decoding a 2 so that this AND gate is only going to happen on step 2 up in here. Okay? I might have to go around here. So go a long way around here. Alright, and I said 5, which is 0 1 0 1. I want to do something with less inverters, so let's say like 7, which would be 0 1 1 1. Does that sound alright? It could be any number that we want. We just make a decoder to work, and a 7 would be only one inverter. Alright, on the least significant bit, because 7 is 0 1 1 1, and so we'll just tile onto here. tile into this net because that's on the most significant bit. And then this is least significant bit, we'll just tile in there. Second bit. And then third bit. Alright, now put test LED. Alright, so now we've got something that'll sequentially happen, and instead of combinationally, it happened exactly, immediately when something triggers it. This will only happen on step 2 and step 7. Okay? So we're going to clear our clear. Alright, so step 1, step 2, step 3, step 4, 5, 6, 7. So now we can have things happen at different points in our circuit. Now, that's just turning a light on it too, but we could have it driving other circuitry that's doing other things. Like step 2, we want this to move from here to here, so we open up some gates. We open up a multiplexer to move certain data onto the line, and we open up another demultiplexer to move into another area, stuff like that. So take a quick video of this, and I hope you have a great, rest of your time, and I really appreciate you going through this with me. And I swear, if my microphone's not working and I just did a 50-minute video, I'm going to be very, very sad. Okay, yeah, it looks like the microphone's working. Thank you. Not that I wouldn't want to do, I don't want to do this again, but I love doing digital. If this does get you interested, like Deeds is free, and I love talking shop, so we could go as far as you want to. Like some classes, we've gotten to the point where we've made a 2-bit microprocessor. All it is a counter, some decoding, and some memory and some multiplexers and demultiplexers. Like if this is something you like, get with me and I can give you some components that are mine, so I can give them to you and you can keep going, and I can keep showing you more stuff, and you can go here if you're not part of my cohort. And there's a lot of information here that's really well written. Okay, so hope you enjoyed yourself. I know it wasn't as much as I enjoyed myself. I absolutely love this. But if you think about it in terms of the secrets. This is what's going on inside. I feel pretty proud myself. You should feel pretty proud. You're doing things that other people, would have no clue about. So that's the end of this video. I apologize it's so long, but I wanted to get as much as I could into it. Okay.